Hello, friends, and welcome to this lesson on chemical reactions, where we're going to talk about the basics of chemical reactions, the different types of chemical reactions, and how we balance them. So first of all, we have some basics here. So any chemical equation is written this way. We have reactants, yield, products. Sometimes we have something above the arrow, and it indicates that that is required to make the reaction happen. The most common thing might be a triangle, which means heat is required. So energy has to be put in. Maybe reactants have to be heated up for the reaction to happen. In a lot of chemical equations, you're going to see the state of matter that the substance is in. So this is shown as a subscript. It can either be S for solid, L for liquid, G for gas, and AQ for aqueous, which just indicates it's dissolved in water. So this is typically going to be with our ionic compounds that are made into solutions. They're dissolved in water. States of matter are important because sometimes the state of matter indicates if the reaction can even happen. So for example, here we have silver nitrate, and it's in its solid form. So it's just powder silver nitrate. And then we have sodium chloride in its powder form, solid. If I put those two things together, nothing happens. We're just gonna have a bigger white crystal pile, okay? But if I dissolve each of these in water and make them aqueous, when they're aqueous, they're broken down into their ions, and when they combine, we do have a reaction in solid silver chloride forms. All chemical reactions, and then therefore the equations that represent them, have to be balanced because they have to abide by the law of conservation of mass or matter. No matter, no atoms can be created or destroyed. They can only rearrange or change forms. So for example here, where we have two hydrogens plus an oxygen makes two waters. So in the reactants, I have 1, 2, 3, 4 hydrogen atoms, and in the products I have 1, 2, 3, 4 hydrogens. 2 oxygens, 2 oxygens. It's just here these hydrogens were together and the oxygens were together, and here they made water. So we always have to have a balanced chemical reaction. And we balance reactions with coefficients, okay? So here are some practice equations. Notice this one is in word form, so of course we're gonna have to write it out first. But here's some practice with balancing. If you don't remember what I mean by this, let's do the first one together, then you can pause and try the rest on your own. So if we look at this first example, I have 1 calcium here, but I have 3 in my products. Well, that is not possible. I can't just suddenly gain 2 calcium atoms. So I'm going to use coefficients to balance. What coefficients mean are your large numbers out in front. So I'm going to put a 3 here. Well, why can't I just put a 3 down there? Because that changes the entire formula. So in a chemical equation, once these formulas are written, I do not alter them. I don't add subscripts to change formulas because they're balanced with charges. So instead, I have to use coefficients. So this 3 now tells me I have 3 calciums, but it also distributes there and tells me I have 6 hydroxides now, because in total I have 3 calcium hydroxides. So when a polyatomic ion stays intact, we can easily just balance the polyatomic. Unfortunately here, hydroxide didn't do that, but phosphate did. So what that means is I can balance phosphate as one thing. So over here, I only have 1 phosphate, but over here, I have 2 phosphates. So I'm going to put a 2 out in front of this phosphoric acid. Now I have 2 phosphates, but I also now have 2 times 3, which is 6 hydrogens, okay? So now on the right-hand side, I have H2O. So I have 2 hydrogens and 1 oxygen. Well, let's look over in the reactants. In total, I have 3 times 2, which is 6 oxygens and 6 hydrogens. Over here, I have 2 times 3, which makes 6 total hydrogens. So combined, I have 12 hydrogens and 6 oxygens. All right, well, if I put a 6 here, now I have 12 hydrogens and 6 oxygens in the product. So this balanced equation has coefficients of 3, 2, 6, and 1. And we don't ever write the 1 because if it's written here, it's understood to be there. So if you'd like to pause and then try the rest on your own and then resume, and I'll go through the answers. So for the second one, we have 8 sulfurs and 3 sulfurs. So a lot of times what you'll start to notice is you can just use patterns. So if I put a 3 in front of this and an 8 in front of this, well, 3 times 8 and 3 times 8, 24. So now I have 8 times 2, which is 16 chromiums. So I'm just going to balance that with a 16. For this one down here, chlorate didn't stay together, so I can't balance it as one thing. But I can look and say there are 3 oxygens, but only 2 in the products. So I'm going to put a 3 in front of that and a 2 here. Now I have 6 oxygens and 6 oxygens. 2 potassiums and 2 chlorines. So if I put a 2 here, I now have 2 potassium and 2 chlorine. We can always check ourselves and make sure it's the most reduced. Well, 2, 2, and 3 can't be reduced any further. All right. This next one, first thing I got to do is I got to write the actual equation out. So iron 3 sulfide is Fe2S3 plus hydrogen chloride yields iron 3 chloride plus hydrogen sulfide gas. All right. So now, notice what I did. When I was writing the equation, I used subscripts when writing formulas, when balancing the small formulas, like we always have, like on your quiz, like anytime we were learning to write formulas. Now that I've written all of them, I'm going to get bigger and balance the big equation with my big coefficients. So I look and I have 2 irons in my reactants and I have 1 in my products. So I'm going to put a 2 here. Now I balanced my iron. But now I have 2 times 3, 6 chlorines. So I'm going to put a 6 here. Well, that balanced my chlorines out, but it gave me 6 hydrogens. Well, if I go to the right and I put a 3 here, I now have 6 hydrogens. Then that gives me 3 sulfurs in the products, which is good because I have 3 sulfurs in the reactants. So now I'm balanced. Last one, I have 2 irons in the reactants. So I'm going to put 2 in the products. Then I have 3 oxygens, 2 aluminums in the product. So I need a 2 here. So 1, 2, 2, 1. All right. So our different types of chemical reactions. We have 6 main types. And I like to use these silly little analogies to help you remember the types of reactions. So the first is a synthesis reaction, which is exactly what it sounds like. To synthesize something is to make it. So a synthesis reaction is when 2 different compounds or 2 different substances, 2 different elements, whatever it may be, come together to make a new element or a new compound, excuse me. So 2 or more things become 1. So the example, when 2 people get married, they become 1 family. So like Kate and Will. Some specific synthesis reactions that you need to be aware of are on this slide. So if you want to write these down, whatever you want. But a metal oxide and a water are going to come together to make a base, a hydroxide base. A non-metal oxide and water are going to come together to create an acid. Okay, now these are just things you need to be aware of or cognizant of. If you ever see a metal oxide and water and you had to predict the product, you know it's going to be a base. Our second type of chemical reaction is a decomposition, which is exactly what it sounds. It decomposes. It breaks apart. It's the exact opposite to synthesis. So I have 1 compound and I'm going to break apart into 2 or more. So my example here is Miley Cyrus was with Liam, and then they broke up. And then I think they got back together, but now as far as I know, they're broken up again, which I don't know why you would break up with that, but anyways. So, broke apart. Some specific decompositions. Carbonates decompose into an oxide and carbon dioxide. Bicarbonates decompose to the oxide, water, and carbon dioxide. And metallic hydroxides decompose into a metal oxide and water. So you'll notice that last one is just the reverse of the synthesis from the prior slide. Our third type is a single replacement. That's where we have a compound and then a singular element, and that one element is going to replace one in the compound. So my example here is, a lot of you probably don't remember this, but it was this huge televised wedding when Kim married Chris, who was a NBA basketball player. Well, then Kanye came in, kicked Chris out of the picture, and now Kanye is with Kim. That's how a single replacement works. We have two main types of single replacements. We have where cation replaces cation. So in other words, two metals are going to swap places. So in this first example, I have zinc is coming and kicking out copper to make zinc sulfate, and now copper is by itself. We also have anions replacing anions, meaning when two halogens switch. So here I have chlorine coming in and kicking out bromine to make sodium chloride, and now bromine's by itself. In regular chemistry, you would have learned about this activity series. And this just shows what the reactivity of metals and halogens. The thing to know is that in order for a single replacement to happen, the singular element has to be more reactive than the one that it is replacing. Okay? Some specific single replacements to know. A metal replaces hydrogen from water or from an acid. When it does that, it kicks out that hydrogen and makes hydrogen gas. So that's when we talk about acids more, that's a characteristic of an acid. When you put a metal down in an acid, you produce hydrogen gas. Or when you put a metal down in water, if it's reactive enough, you'll produce hydrogen gas. So if you've ever seen the videos of the group 1 elements being put in water and then exploding, it's because they are more reactive, and so they kick out a hydrogen. They create hydrogen gas, which is extremely flammable. It also creates heat. It ignites that hydrogen gas, and that's what causes them to explode. Our fourth type is a combustion. So a combustion reaction is when a substance, usually a hydrocarbon, sometimes it also has oxygen, reacts in oxygen gas. That is always going to be your reactant in a combustion reaction. And it forms carbon dioxide and water every single time. It also forms lots of fire and light and boom. All right, so I use this example because I kind of feel like Miley Cyrus combusted. She went from this simple little naive Hannah Montana to licking hammers and riding on wrecking balls, and I don't even know. But you recognize a combustion because it's something burning in oxygen gas and it makes carbon dioxide and water. Our fifth type of reaction is a double replacement. A lot of times we're going to call these precipitation reactions because they form a precipitate. So in a double replacement reaction, we have two compounds. So if you remember, in single replacement, we had a compound and a singular element. Now we have two compounds. And a part of the compound is going to switch places, basically. So A and C are going to swap here. And now A is with D and C is with B. This doesn't happen a lot in real life, but I found an example. If you've ever seen Secret Life of the American Teenager, came out forever ago on ABC Family, which isn't even ABC Family anymore. But these two people were dating. So she got pregnant with this dude's baby, and then she decides to have the baby, but they're not together, and so she this Ben dude becomes her boyfriend. Okay. Well, then dude that got her pregnant is dating this girl. Well, eventually, as the show goes on, he decides he wants to actually be the dad, so they end up together and get married. And then, of course, like any normal person, her ex-boyfriend is now going to be with this girl. Okay, weird. ABC Family shows are weird. But regardless, that's an example of a double replacement reaction. We're swapping partners. Another type of reaction is an acid-base reaction, which is when an acid and a base react together to neutralize or form a salt, which is just another word for ionic compound, and water. All right, so here's practice. I want you to just identify the type of reaction that's listed here. So if you would like, you can pause and then resume and check your answers. So this first reaction is synthesis, decomposition for the second one, double replacement, combustion, single replacement, decomposition, and synthesis. Simple enough. Okay, so now we need to focus on that double replacement reaction that I mentioned is sometimes called a precipitation reaction because it forms a precipitate. So precipitation reactions involve aqueous solutions. So remember back to the slide where I showed you solid silver nitrate and solid sodium chloride together didn't do anything but make a big pile of white powder? Well, if we dissolve each of them separately in water, we now have aqueous solutions. Why do we always use water? Well, water is a really good solvent because it's extremely polar. And these ionic compounds, we know, are made up of a positive and a negative, right? And so the water, which is extremely polar, breaks these apart into their ions. And once they're in their ions, so in their aqueous form, they are now free to combine with new ions. And so that's what happens in a precipitation reaction. We have two separate aqueous solutions, and then when we combine them, if two of the ions together are what we call insoluble, they are going to form a solid. We call that solid a precipitate. So in that reaction that I just showed you, what's actually going on? Well, here, like we said, we had aqueous potassium iodide and aqueous lead nitrate. So what does aqueous mean? Dissolved in water. So in reality, we have all four of these ions. These two are in one beaker and these two are in another beaker. When I add them together, the potassium and the nitrate stay separate because they're soluble. So maybe a potassium runs into a nitrate. I'm more attracted to water than I am you. Breaks back apart. But lead and iodine, when they run into each other, they're like, ooh, I'm more attracted to you than I am to the water molecules, so we're going to stay together, and now they are solid. Okay? So because this didn't change and stayed in solution, this didn't change and stay in solution, the only thing that actually happens is two iodine ions are going to come together with a lead ion to form solid lead iodide. So the first thing we want to practice is just writing the products to a precipitation reaction. So I'll do the first one, then maybe pause, and then check your answers on the second two. So all you got to do is you got to take your metals and just have them swap places. So now I'm writing brand new products. So now potassium is with nitrate. Now the thing that trips students up, you still have to remember how to write formulas. These are brand new products. So it doesn't matter how many there were in the formula on the reactant side, we're making brand new products. So now potassium is with nitrate. Potassium's +1 and nitrate's -1. So this one is balanced. Plus, now we have silver with chlorine. Now that one was easy because they're all +1, -1, so everything is balanced, so I don't need any coefficients. So this is going to remain aqueous, and this is our solid. And I'll explain in a minute how I do that. So if you want, pause, and then check your answers to the last two. So now zinc and barium are going to switch places. So zinc dichromate plus barium nitrate. And again, this one's already balanced, so I do not need coefficients. That one is going to be my solid, and this one's going to be aqueous. Again, in a future slide, we'll talk about how I know that. All right, last one, cadmium and sodium are switching places. So cadmium sulfide plus sodium chloride. Again, just because there's 2 chlorines over here does not mean I put a 2 in the subscript over here. There had to be 2 chlorines over here because cadmium is +2 and chlorine's -1, so I needed 2. Over here, sodium is +1 and chlorine's -1, so I don't need a subscript. What I do need is a coefficient. Because there's 2 chlorines over here and 2 sodiums over here, I need to put a 2 in front so that my entire equation is balanced. This is going to be my solid, and this is the aqueous. All right, as promised, how did I know what was solid and aqueous? Well, precipitation reactions occur when one product is insoluble. Insoluble means will not dissolve. Now, I'm going to go ahead and throw this out here. Everything dissolves a tiny bit. And we're going to go through an entire unit where we talk about solubility. But for right now, we're going to just call them insoluble because the amount that they dissolve is so tiny that we're just going to right now talk about it being insignificant. So for now, some products are going to be insoluble, meaning that they don't dissolve in water. So when they come together, they stick together and form a solid. So how do I know which ones these are? Well, you're going to memorize them. Now, before you freak out, okay, just know a couple things. Number one, you're never going to have a precipitate reaction where one of them isn't a precipitate. So in your products, you are always going to have one that's aqueous and one that's solid. Number two, if you can memorize the things that are always soluble and identify that in your product, then you know the other one is your solid. So here's some examples of the solubility rules. So again, if you can memorize, all right, if I have group 1, it does not matter what it is with, it's going to be soluble. So ammonium in group 1 will never, ever, 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 ever be a solid. I repeat, do not tell me that like sodium anything is solid. It's never, ever, ever solid. Got it? Got it. Okay. Neither is anything with ammonium. Now, halides are typically soluble, but you have these exceptions. Acetate, always soluble, bicarbonate, nitrate, always soluble, chlorate, always soluble, and then sulfate's a tricky one because we have these exceptions. Okay? So if you can really memorize this part, then you know anything else is your solid. So we have 3 different ways that we can write a precipitate reaction. We can write what we call the molecular equation, meaning we're just writing them as their formula. And we use this to indicate that they are aqueous or solid. Or we can write what's called the complete ionic equation. This one shows more of the reality, I guess you would say. Because these are aqueous, we know they're not actually together in a compound. They're separated into their ions. Okay? And then in the products, we have this one is aqueous, so it's still separated into its ions. But this one is solid, so we don't write it as separate ions because it's not separate ions. It's a solid. So ionic compounds, when they're solid, they're together, not ions. The ions are canceling themselves out to make a neutral compound. But when they're aqueous, they're separated into their ions. The final way, and what's probably the most useful way, is called the net ionic equation. What that does is it takes away what we call spectator ions, or it takes away the ions that didn't actually do anything in the reaction. So sodium stayed aqueous, chlorine stayed aqueous, but what did react were 3 hydroxides and an iron to make iron hydroxide. Okay, so let's practice writing all 3 types of reactions. So I'm starting with aqueous iron 3 sulfate, which would mean I need 3 irons, 2 sulfates, plus aqueous potassium sulfide, Now, what is that going to make? We're going to swap places. So I'm going to have iron, iron 3. So Fe2S3 plus K2SO4. Potassium, it's in group 1. It's never, ever, ever insoluble. So this is aqueous, so this has to be my solid. Okay, so there's my first type. There's the molecular equation. Now I'm going to write my full ionic equation. So Fe2SO4 3 means I have 2 irons plus 3 sulfates plus 2 potassiums plus 1 sulfur. Oh, Mrs. Wilkins, I didn't balance my equation at the top. All right, let me hop back for a second. This isn't balanced. Here I have 2 potassiums, I have 2 on the right, but I've got 3 sulfates and only 1 on the product, so I'm going to put a 3 right here. 3 sulfates, 3 sulfates. 3 times 2 makes 6 potassiums, so I'm going to put a 3 here. 6 potassiums, that's now balanced, and then 3 sulfurs, 3 sulfurs. Okay, so let's fix my mistake. Now I have 6 potassiums plus 3 sulfurs. This is a solid, so I'm not going to break it up because it's not ions. But this one is still aqueous, so I am going to break it up. Now notice, when I'm writing ions, ions have charges. You have to make sure that you include your charges. All right? Now my third way of writing it is the net ionic. So I'm going to take away the spectators. I'm going to ignore things that didn't actually form the precipitate. So you can kind of think of this 2 ways. You could either cancel out the things that stayed the same, or you can kind of write this backwards. I know my product is Fe2S3. Well, what makes Fe2S3? 2 irons and 3 sulfurs. Good? Cool. All right, last example. I have aqueous lead 2 nitrate plus aqueous sulfuric acid. Ic means it came from sulfates. Now I'm going to trade partners. So now I have lead 2 sulfate plus nitric acid. Well, nitrates are always soluble, so this one has to be aqueous, which means this one has to be my solid. Now, let me look to see if I'm balanced, and I am not balanced. I have 2 nitrates in the reactants, but only 1 in the product, so I'm going to put a 2 here. Well, now I have 2 hydrogens, but that's good because I had 2 hydrogens in the reactants. 1 sulfate, 1 sulfate. 1 lead, 1 lead. Now I'm balanced. Now I'm going to break anything aqueous up into its ions. So lead 2 plus I have 2 nitrates plus 2 hydrogens plus a sulfate. Now I'm not going to break up my solid, but I am going to break up the one that is still aqueous. Now finally, my net ionic, I'm just going to write down the things that formed my precipitate, because that was the only actual reaction that occurred. Very good. This has been another wonderful lecture with Mrs. Wilkins, and I'll see you next time.